So section 4.2 is all about finding the area beneath a curve. In the previous video, what we did, we found the approximate area beneath a curve because we don't have a geometrical formula for the area beneath this particular f of x. So we just chopped it up into rectangles, 4 to be precise. And we did it two different ways. We did an overestimate and we did an underestimate. And then I said, well, my best guess for the area beneath this curve is going to be the average of these two values. That's an approximation. It's a pretty good one. And if you want them to be better, you would use more than 4 rectangles. You would use 8 rectangles. You would use 16, 32, 100, 200, 1,000, 1 billion. The more rectangles you use, the better the approximation. Of course, the problem is the more computation, the more multiplication and addition you need to do, and then it just gets to be too much. So what I want to show you now is I want to show you how to extrapolate what we did, finding the approximate area under the curve, to get the exact area under the curve. Now there's value in this, in having the area beneath the curve. There are many real-world problems that require that area beneath a curve, one of which would be force times, or force versus time. If you actually looked at the force versus time curve of an automobile accident, you would see that the force peaks up very rapidly and then slowly comes back down to the x-axis as the force dissipates to 0, and that's the end of the accident. Turns out that the area beneath that curve is the energy, or the kinetic energy. So there is certainly value in knowing the area beneath that particular curve as well as many others. So let's see if we can find the exact area beneath the curve. And I'm going to use the same example I used in the previous video, the same function, because we've already worked on it. We have an overestimate and underestimate, and then we average them together, of course, to get our best guess. So let's see how close we were. So let's take a look at this function. F of x is minus x squared plus 4. And let's discover how we would find the exact area beneath the curve using sums and sigma notation. We're going to be using sums because we're going to be adding areas of rectangles up, but not 4, not 8. We're going to actually add more than 100, more than 1,000,000, more than 1 billion. Somehow, we're going to add up an infinite number of rectangles, where each rectangle is razor thin. Delta x is going to go to 0. So if we take a look at this curve, the y-intercept is up here at 1, 2, 3, and 4. So we'll place our y-intercept here. If you find your x-intercept by setting y to 0, you're going to find that that's plus and minus 2. And then it's an upside-down parabola that comes down here to 2. And the area I'm interested in is right here. Now, if I do slice this up, because that will help us figure out what we're going to do here. I've sliced it into 2 intervals, but I want to do better than that. Let's slice it into 4 again. You'll remember that we did an overestimate and an underestimate. And the overestimate was 6 1/4. The underestimate was 4 1/4. The average, which is our best guess, was area 5 1/4. So right now that's our best guess, but I'd like to see if we can get an exact value. Now, rather than just simply breaking this up into 4 rectangles and labeling these as 1/2, 1, and 3/2, which we did before, I'm going to be a little more generic about this. I'm going to label this A. I'm going to label this ending point as B. Of course, A is 0, so I'll put a 0 there. But let's label each of these x values like this. This is x0. This one here is x1. This one here is x2. Here's x3. And then finally x4. So each x value has its own terminology. X0, 1, 2, 3, and 4. Let's zoom in on that. Now it's getting a little tight in there, but I think what I'm going to do is perhaps zoom in on that little area there. Okay, so here's my 0, Here's my 2. And here's my 1. And here's my half. And here's my 3/2. So yes, I know there's a curve up there, but really one of the most important things to do here is to actually be able to come up with a formula that I call the pointer. And what it'll do is the pointer will point to one of these specific x values. Now, before we do this, let's actually get in here and calculate our delta x, because luckily for us, they're all the same. So delta x is the same for each interval. Delta x is the difference between these two x values. Now, what I want to do here is I'd like to come up with a couple of formulas today. The first formula is, can we come up with a formula for delta x? Now, for any area beneath a curve, we're always going to start at x equals a and stop at x equals b. So I'll call that the master width. The master width is b minus a. And that's the width of the entire problem from the beginning to the end. So the master width for this problem is b minus a, and they'll all be b minus a. Now I want the number of slices here to be denoted with n, and that's going to be the number of slices, n. I know n is 4, but let's leave n open so that we can do n equals 8 later, or n equals 100, 1,000,000. Ultimately, I want n to go to infinity. And think about what would happen if you did make n go to infinity. What would happen to delta x? Well, there's so many slices that delta x would have to squeeze down to be 0 in order for all of those slices to fit. Now, let's calculate delta x. Delta x is the width of just one of my intervals here, or one of my rectangles. Delta x should be the master width divided by n slices. This is an important formula. You're going to see it over and over again. We use the same formula for pretty much every problem. The width of one rectangle is the master width divided by the number of slices. Now, for this particular problem, delta x would be 2 minus 0 over the number of slices, which is 2 over the number of slices. Now, I realize that n is 4. 1, 2, 3, 4. So 2 over 4 is 1/2, and that does make a lot of sense. 1/2 plus a half plus a half plus a half gets you to 2. So that works out really well. Now, the next thing I'd like to be able to do here is establish what I call the pointer. And the pointer is what allows me to point to any specific x value anytime I like. I don't want to use some of the information that we have, which is a, and I want to use delta x. So I know the book calls these pointers c sub I. I like to call them x sub I. So let's use x sub I instead. C sub I, x sub I, same thing. They're not critical numbers, and that's maybe why I don't like to use the c. But I've already called them x0, 1, 2, 3, and 4, so I think x sub I is a better way to label these for us. Now, I want you to think about something. If I said, can you get me to x3, what would be a good way to do that? Well, a is going to be given to you, so you could literally start right there and then add your way over there to x3. And how would you add your way over there? Well, you would add 1, 2, 3 delta x's. Be a great way for you to get to x3. And this is before I even know what delta x or a really are, but it's a great formula for that. So I think if you extrapolate that, what you discover is that x sub I, x sub anything, is always start at home at a and add your way over to that x sub I by adding that many delta x's. And therein lies another extremely important formula for finding the area beneath a curve. They both make sense, really. You know, delta x is b minus a, master width, sliced into n slices. That makes sense to me, and it worked for our problem. The pointer, x sub I, points to those x values pretty successfully. You want to get to a specific x value, start at home, that's A, and then add that number of delta x's, and you'll land right on that particular x sub I. So the pointer seems like it's working as well. So now we need to use these and formulate a way to calculate the exact area. Now, the first thing I'm going to do is talk about how we would just compute area using maybe even my 4 rectangles here. So again, the curve lives right in here. Oops, more like this. Okay, it comes down here to 2, goes up here, and then we slice and dice into 4 slices. And it doesn't really matter which version you use, the over or the underestimate. So I'm going to use the underestimate. I'm going to use the under by using, because I have a choice in this interval to take the high or the low y, and I'm taking the low y value. I'm taking the low y value. See, this one doesn't even get me any area. Well, I want you to see what I just did to calculate the underestimate. The underestimate is equal to, well, let's see here, x0, x1, x2, x3, and x4. What did I do here? I calculated the area of each rectangle. Let's start with the first rectangle. The first rectangle had a height and a width. The second rectangle had a height and a width. The third rectangle had a height and a width. And finally, the last rectangle had a height and a width. Now, what was that height? Well, take a look at where I got it from. I went to x sub 1, and I reached up, and I got my y value. So how did I get my height? I did the f of x1. What was the width? Just delta x. Just delta x. Plus, how did I get height 2? Well, height 2 is right here, and how did I get it? I went to x sub 2, and I reached up, and I got myself a y value. Functions do that for us. That's what gets us our y value. So it's the f of x2 times delta x, plus the f of x3 times delta x, plus the f of x4 times delta x. So really, I'm adding heights and widths together. We can use a sigma right here. And the sigma I'm going to use is a method of adding multiple things together. And I'm going to cycle I from 1, I guess I can go to 4 in this case. And what am I summing? Height times width. And what is the width for every single one of them? They're all delta x. And what's the height for every single one of them? F of x sub I. Now, instead of just going from 1 to 4, instead of selecting n to be 4, let's leave that open-ended and make that n. So therefore, I can choose n later. And I can choose n to be 4, 8, 16, 100, a million. I'd really like it to be infinity. Because think about it. The more slices you have, the thinner they are, and the less of this blockiness you'll get. See this blockiness up here? We're missing these areas up there. And we're missing this whole piece over here. But the thinner you make them, what you're really doing is you're lining up these hair-thin lines that are tiny, thin rectangles. And then we start eliminating the error. So what do you think the exact answer would be, therefore? Because we know that when we went from 1 to 4, we did not get an exact answer. We got an under approximation. If I went from 1 to 8, I'd still have an under approximation. It would be better, but I'd still have an approximation. If I went from 1 to 100, 1 to 1,000, 1 to 1,000,000,000, these are all rectangles. They're all approximations. So here is the third all-important formula for this section, and that is that ultimately I want an infinite number of rectangles, and there's only one way to get to infinity, and that's with a limit. So it's going to be the limit as n goes to infinity of the sum of these rectangles, I equals 1 to n, of height and width. And I think we've done a pretty good job piecing this formula together, starting with really height times width, and then sigma to add them all together, and then adding the limit so that I have ultimately infinite number of rectangles. By the way, you don't have to put this under here, but just as a little reminder, if n's going into infinity, I think delta x must be going to 0. Something to keep note of. All right. Now, can we use all of that to get the exact precise area beneath this particular curve, which is 4 minus x squared, from 0 to 2? Remember what we did when we overestimated and underestimated. I only used 4 rectangles, so they were pretty gross approximations, but I got 6 1/4 and 4 1/4, average them together, and I got 5 1/4. That was the best guess. It's still an approximation, it's still not exact, and the only way to make it better is to put more rectangles in. So it would just be a lot of work to go to, even to n equals 8, it would be a lot of work to do 8 function valuations. And so we're not going to do that. We're going to go right to the exact answer, which is n approaching infinity. And the thing is, with limits, we can actually do that. We can pull that off. So here's how it works. The function is minus x squared plus 4, or if you like, 4 minus x squared. Either one is fine. We want to start at a equals 0. We want to stop at b equals 2. And I'd like the area beneath this particular function. And that's all you really get. The first thing you should calculate would be delta x, which is the master width divided by the number of slices. The master width is 2 minus 0 divided by the number of slices. Therefore, delta x is 2 over n. This is not a good time to plug n equals infinity right now. If you plug n equals infinity, which is ultimately where I'm headed, you're going to get delta x equals 0, and then, therefore, the area of each rectangle is 0. And so your area will be 0. And I don't think that's the exact area beneath this curve. The next thing you want, the pointer. I'd like to be able to point to each and every x value, x1, x2, x3, etc. And remember, we came up with a formulation for that. It was, and I'll box these up because these get reused. So x sub I, you're trying to get to x sub whatever. I'll put this back down here. You're trying to get to x2. How do you get there? Well, start at home. A will be provided to you. And then add 2 delta x's, and you land right there. So the pointer ended up being, I would always start at A, and I would add that many delta x's to get to where I'd like to be. Again, a nice reusable formula. Now, this is specific to our problem. B minus A is 2 over n. Do not plug n equals infinity until you run the limit. All right, so now let's formulate x sub I. X sub I is our starting point. 0 plus I times delta x, which would be 2 over n. So I got a nice expression for my pointer, and that's 2i over n. And that's specific to the problem, so we'll star that, and we'll be able to use that in our problem. Now let's see if these make any sense. Let's go back to the n equals 4 case and see if this thing works. If we did end up using n equals 4, 2 over 4 was 1/2, and yes, indeed, you remember delta x was 1/2, so that makes sense. If indeed n equals 4, this is 2i over 4. This is I over 2. X sub I is I over 2. I over 2. So, okay, I'd like to go to x3. 3 over 2. If you remember, x3 was 3/2. And I want to go to x4, which is the last one. 4 over 2 is 2. And if you remember, of course, that's b. That's the very end of the problem. So it really does work. That formula works very well for our n equals 4 case. It'll work for any particular n that you choose. All right. We're almost there, guys. Because now the ultimate in finding exact areas is to say, well, I know that the area of each rectangle is a height, and there's only one way to get height. That's a y value. You need the function. And you want to evaluate the function at each individual x sub I, so we're kind of marching along, getting our different heights. And then we multiply that height by the individual width of each rectangle, which is delta x, okay? Now that's only one rectangle right there. I want them all. And the way to get them all and to sum them together is to use that sigma and sum from I equals 1 to n. So this would, if this n was 4, you'd add 4 rectangles. But the ultimate in getting exact area is to push on that n right out to infinity. And that should get me the exact area. All right, let's see if we can do this. Now I want you to copy limit and sigma until you have simplified sigma, first of all. And the way we're going to simplify sigma, I can't really run a sigma in my head, and I don't want to run it manually. We don't want to sit there and do 1 plus 2 plus 3. And here's the real reason why, because I'm going to ask you to add an infinite number of items. So not only do I not want to do that, it's actually impossible to do that. So sigma will get simplified by using those summation formulas. Those are going to come into play. I need you to copy limit over and over and over until the very last step, when you actually, using direct substitution, make n go to infinity. If you make n go to infinity too early, area is not going to come out. It's going to come out to be probably an indeterminate form or 0 or something like that. So I wouldn't do that until the very end. So we're going to save the limit and sigma for the end. Let's work in here. So the exact area is the limit as n gets pushed to infinity. So there'll be an infinite number of rectangles, no blockiness, no error. It's going to give me the exact answer. We're going to sum from I equals 1 to n the f of x sub I times delta x. Well, we have a formula for x sub I. It's right here, 2i over n. We have a formula for delta x. It's up here, 2 over n. Now, the first thing I'll point out to you when you do these is don't multiply this together. In calculus and math, any math that you do, the arguments are so well protected, they're in this steel vault right here, okay? That means do not ever distribute into an argument like that. I know it's tempting. In fact, it's so tempting, I'll often take 2 over n and I'll put it out in front there when that temptation is there. But I think we can do this because the next step is, actually, we're going to run this from here backwards. So we're going to start with this f. F is a function. The function wants to be executed. So let's copy the limit. Let's copy the sigma. And let's execute the function. Now, what does this particular function do? Okay, go back up here and take a look. This function says I always start with the number 4 and I take away input squared. If you put a 3 in here, it's going to be 4 minus 3 squared. If you put a letter a in there, it'll be 4 minus a squared. If you put one of these things in there, the result will be 4 minus input squared. That's how functions work. Okay, we replace the letter x with the contents inside the argument. All right, same thing I said before. Let's wait on these. Let's work our algebra over here. Now there's no f anymore. There's no argument really except for here. Let's simplify that first, and then I will be able to multiply by 2 over n. So let's go ahead and see what we got. So this is 4 minus 4i squared over n squared. Multiplied by 2 over n, of course, and now you can use the distributive law because it's just multiplication. There's no function in the way. So let's do that. Where are we? We got to copy our limits and our sigmas until we're ready to eliminate them by using the summation formula and eliminate the limit by actually using direct substitution once we're ready for it. If you try to directly substitute infinity in now, it's not going to really work too well. All right, so let's see what we get here. We get 8 over n minus 4i squared over n cubed. That's your algebra right there. Now the process I'm showing you is truly the same for almost all of these problems. Delta x is b minus a over n every time, but calculate b minus a. X sub I, that little pointer, is a plus I delta x every time. So put in your a, put in your delta x. I will tell you they are more difficult when a is not 0. That gets to be a little more challenging, but it is doable. And what did I do next? I executed the function, f of x sub I. And I put the x sub I in there, and then I executed the function. That's what I did right about here. Execute that function. And don't forget to do that. That's important. 4 minus input squared. Now I'm doing my algebra, and I'm simplifying. Now the nice thing about sigmas is that each one of them gets their very own sigma. So it's going to be the sum of 8 over n minus the sum of 4i squared over n cubed. Now what? Okay, we need to simplify these. We need to use those summation formulas. Now, there's one rule that works so well in almost everything we do, and that is about constant multiples. Constant multiples work really well with derivatives. You just drag them in front of the derivative. Constant multiples will work very well when we get to when we've done the antiderivative, and constant multiples will park in front of the antiderivative as well. Constant multiples also can be dragged in front of sigmas. So constant multiples are great. They always just slide themselves out front and wait for the answer inside. So what is a constant multiple in this problem? Now, it might not seem like n is a constant because n is being pushed to infinity. But before we push it to infinity, really what's happening here is n is being literally assigned values. Like n is being assigned 4. And then we get a computation and we see what that area would be at 4. Then n is assigned 8. And then we do the computation and we get an area for that. It's a better area. And then we do 100. Then we do n equals 1,000,000. And then we look at that area. And really what limits do, they watch the trend in area. And then they project what would happen if n were truly infinity. So n is kind of assigned a value each time those are made. So if you think about it, let's just do the n equals 4 case. I equals 1 to 4. N is 4 for that particular version. And so every time we go through sigma, it's 8 over 4 plus 8 over 4 plus 8 over 4 plus 8 over 4. So n is really a constant. Over here, we've got an I. We have an I squared. I is not a constant because you can imagine this sigma kind of clicking I from 1 up to n. So let's make n equal 4. But I equals 1 up to 4. So the first time around, it's 4 times 1 squared over 4 cubed. Next time around, it's 4 times 2 squared over 4 cubed. Next time, 4 times 3 squared, etc. So I think you could, really think about I as not being a constant. I is definitely changing and really can't be dragged across that sigma. But it is interesting to note that n is constant. Once an n is chosen, it's locked in place. And every time n is called for in the problem, it's the same n. So it actually is a constant. So let's drag the constants out front. These are both constants. So I'll take the 8 and the n and drag it out front. Well, that's weird. There's nothing left. Well, we know there's always a hidden 1 left for a problem like that. Let's take the 4 and the n cubed and drag those in front of my sigma. What's left behind is the sum of I squared. We're pretty close because I recognize those sums. This is just the sum of a constant. And if you remember your summation rules, remember what they look like. If I did sum a constant, c, from 1 to n. It's c plus c plus c plus c plus c n times. In other words, it's n times c. So that should just be n times 1. Over here, we have another summation that looks awfully familiar, and that was the sum of I squared. Now, if I had to do it manually, it would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, and we'd be here all day, especially since n will ultimately be infinity. It's impossible. But we do have a formula that does all the work for us. I call this my little summing computer right here. It'll compute it for me immediately without having to do all that work. Now it's time to get rid of these sigmas, guys. Let's reduce sigmas using our summation formulas. Now the limit gets copied over and over. We're not ready for that limit yet, so let's copy it. Now here's what I get. 8 over n is parked out front and waiting. What's the sum of a constant again? Well, here it is. It's simply n times c. N times 1 is n. Minus 4 over n cubed. What's the sum of I squared? Well, unfortunately, it's this formula here, so I'll write it down. n plus 1, 2n plus 1, all over 6. Well, at least you don't have to worry about sigma anymore. So let's see what we got. I got some nice cancellation going on here. I see this n will cancel with this n, leaving me with a squared underneath. I see that these two will cancel, leaving me with a 2 on top and a 3 on the bottom. So I'm almost ready for this. This is a big 8. And what I'm getting over here is minus 2, 3n squared. See, that's what's left. There's my 2. And I'd like you to FOIL this thing out up here to see what really we have. So I have 2n squared. I have a 2n and a 1n. That's 3n. And I have a 1 times 1, which is 1. We're still in a situation where sending n to infinity will cause you a lot of problems. If you send n to infinity right now, here's what happens. Infinity over infinity. It's just not going to work. So I need to do some reducing up here, and let's do that before we even touch this with n being infinity. Now look what you got here. 2 times 2 is 4n squared over 3n squared, and it looks to me like those cancel right out. So now we're going to do 2 times 3, which is minus 6n over 3n squared. I'm giving each term a copy of the denominator. And finally, minus 2 over 3n squared. Well, let's see where we're at here. The limit as n is pushed to infinity of, well, let's do this 8 minus 4/3. That's just a number. And maybe a good way to do that is to do 8 over 1 and make it 24 over 3. That's going to be 20/3. Minus 6 over 3 is 2 over n. Minus 2 over 3n squared. And now we're in a great position, and that position is to simply send n to infinity now. And you know what's going to happen, right? 2 over infinity, 2 over infinity. The answer is 20/3. The answer is 20/3. So the exact area beneath this curve from 0 to 2 apparently is 20 over 3. Now let's see what that truly is. 6 2/3. 6 2/3. So we found a method for getting the exact area underneath this curve. And the way we did it was we found delta x, which is the width of each the width of each rectangle, and we found pointers to all of our x values. And I used the limit method. I used sigmas. But if you break it down, it kind of runs backwards. Delta x is the first thing we figure out, b minus a over n. X sub I, the little pointer, is the next thing we figure out. That's a plus I delta x. Then we stick that into the function to reach up and get our y value because you need a height. Don't forget to execute your function. And then finally do the algebra. Multiply delta x in, do the algebra, and then finally you can, well, wait a second. Before you do the algebra, you need to translate your sigmas into their summation formulas, finish the algebra, and then you can send n to infinity. So I think that was an interesting problem where we were able to not only approximate the area to the curve, but we actually now have the exact and precise area under this curve, 6 2/3. Okay. The next thing I'd like to do is I'd like to try to look at finding an area, and before I do that, I want to check one thing on this here. I want to make sure that we got this exactly right. But I'm just checking here. 2 times 2 is 4, and I believe that is correct. But I'm seeing an error in here that I'm trying to resolve, and I'm not sure exactly where it's coming from. Give me 1 second here to track that error down. 4 over n cubed comes out. Sum of I squared is n plus 1, 2n plus 1 over. I got that. Because I'm believing that this should be an 8 and not a 4, and I'm just trying to find out why. And the reason I'm suspicious of this is because that is not what I thought it would be. I thought it would be closer to 5 1/4, because if you remember, we approximated 5 1/4 for that. So I'm just double checking my work. Give me 1 second here, make sure I did this right. I think maybe I see the error here. This should be 4 times 2 is 8. Did we do that? And we didn't do that, guys. Nobody's perfect, and I think we can fix this. So I missed one multiplication here, and I see where I missed it. It's right here. So this 2 over n needed to distribute. I knew something was up. This should be 4 times 2 is 8 over n. This should be 4 times 2 is also 8i squared over n cubed. So if you caught that, nice job. I got to change these all to 8s. Let's get in there and change them all to 8s. Sorry about that. So the 8 pops out front. Okay, and this also becomes an 8. That makes this a 4. That makes this a 4. And actually, we're back to an 8 again. We're back to an 8. So, here's the correction. This is 24 minus 8. And 24 minus 8 is 16. So this is not 20/3. This is 16/3. And the answer is 16/3. That I'm much more happy about. So 16/3 is 5 1/3. So we fixed it. We found the error. And I'll tell you, I'm glad that actually happened, because one of the things that we like to teach in math and calculus is the reasonableness of your answer. And my problem with the answer that I got was it wasn't reasonable. We had an overestimate and we had an underestimate from the previous work that we did. The overestimate was 6 1/4, and that was supposed to be an overshoot. In other words, the real area was supposed to be less than 6 1/4, so we just got 6 2/3. And that's over the overestimate. That's impossible. The overestimate is supposed to be a ceiling on area. The underestimate is a floor. And then we averaged it together, and we got, remember, 5 1/4 was my best guess. So I was really expecting the area to come in around 5 1/4. So now that we've corrected that one little error, the area actually did come in, not at 5 1/4 though, at 5 1/3. So that's a better formulation for area. It's exactly right. There is no approximation to that. Now the last thing I'm going to leave you with is we also like to find the area up against the y-axis. Not as often though. So we don't do that very often. So I'm going to look at a function of y. And the example I'm looking at is on page 262. And it's just not something that we often do. And things are slightly different. So this time we're going to have a curve like this. We're going to go up to the point 1, 1. And I'm going to ask you for this area right here, up against the y-axis. And the way we're going to do it is going to slice in the y direction. So now, things are a little bit different. These are not delta x's anymore, they're delta y's. These are not heights anymore, these are actually x values. So, first of all, let me give you this function. This is a function of x, and it's going to be the square root of x. Y equals the square root of x. If we square both sides, you discover that y squared equals x, or x equals y squared. So it turns out that x is actually a function of y, and then it's y squared. So it's a different kind of function. It's a function of y. So x can be determined for any given y value. So we're actually going to do it using y values. This would be y0, this would be y1, y2, y3, y4, all the way up to y sub n. These are all my delta y's. These are my widths. So let's see if we can put this together. Can I get the exact area, meaning in here? If I did the area under the curve, you can see that that would be a different space. In fact, there's more area under the curve than there is up against the y-axis. Now, if you really think this through, and you don't want to do it on its side like this, then there is actually a method of doing it the other way, and that is do it the traditional way. And if you do it the traditional way, you will get the area beneath the curve. But that's not what we want. We want this area. So why don't we just take the big square here, 1 by 1 square, which would be 1 times 1 is 1, and subtract this area out. That certainly would work, but I want to show you how to do it this other way, on its side. So here, let's look at some of these rectangles here. Here's one right here. So what's going on is I'm actually using y3 here, but I'm reaching over and I'm actually trying to calculate x3. And x3 would be calculated by using this. So the exact area under this curve would be a sum from I equals 1 to n. Oops, I missed my limit. Hold on. My area is a limit as n approaches infinity of the sum I equals 1 to n, and let's see what we're going to do here. Each width is now delta y. Each height, well, it's not a height. It's an x value, okay? And how do you get your x value? By picking a y value and putting it into the function. That's how we get x values now. So we do the f of y sub I, let's say. This is still a, this is still b, and so really, the formula for delta y is the same as the formula for delta x. Delta y is b minus a over n. b minus a would be 1 minus 0 over n. It's just 1 over n. So delta x, delta y is kind of the same formulation that we would use. Now I need a little pointer that points to these little y values, y sub I. How do we do those pointers? Well, just like the other way, we start with A, and we add I times, well, not delta x, these are all delta y's, and A is y value 0, plus I times delta y, which is 1 over n. So the exact area on the side of that curve, from n going to infinity, we would sum I equals 1 to n, the f of y sub I. Well, here's y sub I that we just formulated, times delta y. And you see, it's kind of the same thing. It's very similar. We need to now execute a function, but it's actually a function of y. So, because what we need are these x's. The x's are really what we need to get that dimension of the rectangle. So what is x? It's a function of y. It's actually just y squared. It's y squared. So function is to square things. Square things. I executed my function. I squared what was inside of it, without forgetting there is also a 1 over n out there. So what is the area up against the y-axis? It's the limit as n approaches infinity of the sum from I equals 1 to n of I squared over n cubed. Now remember, for sigmas, n's are considered to be constant. By the way, isn't it interesting that there's no x and y left here? It's just a sigma, i's, and n's like before. 1 over n cubed comes out front, and all you really need to do is do the sum of I squared. I will tell you that all of these problems lead us to the summations that you're familiar with. The sum of I, the sum of I squared, the sum of a constant, even the sum of I cubed pops up now and again. But we have formulas for those. The formula for this one is n plus 1, 2n plus 1 over 6. We've done that one before on the previous problem. We've also done this before, where the n's, some of the n's cancel, and we've also FOILed this out before. So 2n times n is 2n squared. FOIL it out, you get 3n plus 1 all over 6n squared. My recommendation, split it up. So 2n squared gets a copy of the 6n squared. 3n gets a copy of the 6n squared. And 1 gets a copy of the 6n squared. Well, simplify. It's the limit as n goes to infinity of 1/3 plus 1 over 2n plus 1 over 6n squared. And you know what? We're going to send n to infinity anyway. So what's going to happen to these two is they're going to go to 0. And I just found the area up against the y-axis. Now, if you look back at the picture, 1/3, that sounds about right. If that's 1/3, this must be 2/3 right here. Now, I don't have time to do the area beneath the curve. We've run out of time. But if I go through the whole process, I'm pretty certain you're going to find that the area beneath that curve is 2/3. So anyway, that is another thing that we do. We don't do that one very often. So I would focus my energy on delta x and x sub I, but it does work if you need to do it in the y direction as well. Now we're going to move forward to the next chapter. Things do get a little more complicated when it comes to these sums, because at this point we've been using delta x constant. They've all been the same. But now what we're going to do is make delta x variable, and that definitely makes things a little tougher. We call them Riemann sums. So stay tuned. Check out the next video concerning Riemann sums, which also leads us to indefinite integrals, and that brings us to what we were doing with anti-differentiation. We were doing indefinite integrals, and now we're going to do definite integrals to find area beneath a curve. And that's when calculus starts to make things a lot easier. It really does. So we'll check you out in the next video.